Welcome back to the Deep Dive, where we take complex topics, gather the best source material, strip away the jargon, and give you the essential knowledge you need for those critical aha moments.
Today, we're embarking on an ambitious adventure into a realm you inhabit every single second of your modern life. Digital Wonderland.
That's right.
We are tearing down the walls and looking at the fundamentals of the computer. Our goal isn't just to define the machine, but to truly understand the core structure, the invisible functions, and the pervasive real-world impact of these super smart sidekicks.
Yes, the mission today is to unpack what these ubiquitous machines actually are, what they do, and maybe more importantly, what their limitations are. We know our listeners are already well informed, so we aren't starting from scratch here.
Right.
We're looking past the glossy marketing, past the operating system interface, to the core architecture. What are the logical bones of the machine?
This deep dive is absolutely essential because understanding the core mechanics, the four pillars of computation, input, processing, storage, and output, is really the key to recognizing technology that is, well, hiding in plain sight.
Hiding in plain sight, I like that.
It's the difference between seeing a traffic light and understanding that a microcomputer is controlling the flow of commerce,
Mhm.
or seeing a pacemaker and knowing a tiny processor is monitoring and commanding a heartbeat.
Okay, so let's unpack this with a foundational analogy. It's useful, but maybe only as a starting point.
Sure.
Think of your own brain. Your eyes and ears are the input. They're taking in sensory data.
Right.
Your brain is the immensely complicated processing unit, making sense of all that data. Your memory, both short-term and long-term, is the storage.
Hmm.
And your voice or your physical movement, that's the output. It's how you communicate the result of that internal process.
So a computer mimics this exact logical cycle.
Exactly. But it translates it into instructions carried by electricity and code. It's a literal simulation of thought.
And that framing, I think, allows us to immediately move into a more architectural discussion because while the analogy holds, the architecture itself is much more rigid, much more structured than the human brain.
So let's start at the very beginning. If we strip away all the software, all the apps, all the internet connections, what is the hardline, fundamental definition of a computer?
Fundamentally, a computer is simply a machine that follows instructions or programs to perform specific tasks. And it does so with immense speed and, this is key, predictable accuracy.
Predictable accuracy.
The key concept here is programmability. It's the ability to change the instructions to perform fundamentally different tasks that elevates a computer above a specialized machine, like a toaster.
A toaster only toasts.
Right. That's its one job.
And without those programs, the machine is completely inert. The source material draws a really strong distinction here. You have the hardware, the physical machine, the wires, the chip.
Chassis, yeah.
And then you have the software, which is the intangible set of instructions, the programs. It's like a beautifully built bike without pedals or a chain.
That's a great analogy. It has all the components, but no mechanism, no instructions to actually achieve motion.
And the beauty of modern computing isn't just the raw power of the hardware.
No, it's the logical structure and sheer complexity of the software it can execute. We've moved from simple arithmetic instructions to programs that can model entire planetary climates or generate photorealistic virtual worlds.
The sophistication is in the logical sequence of instructions we feed to the silicon.
Exactly.
Okay, here's where it gets really interesting, because we have to address the biggest misconception that I think plagues the public understanding of technology.
The screen.
Thinking the computer's just the screen.
Oh.
When you look at your phone, you see glass and light, and you assume that's the whole device.
And that mistake immediately limits our understanding of technology. The screen, whether it's an enormous 8K monitor or a tiny digital readout on your microwave, is only the output mechanism.
It's just a window.
It's a window, a single point of sensory interaction. The real computation is happening inside the case, where all these components are working together dynamically.
Yeah.
We have to train ourselves to recognize the entire process, not just the glossy final product.
That context is so crucial. And it's why looking at the historical scale shift is such a powerful teaching tool. 100 years ago, no one would have mistaken the computer for its screen.
Because the computer was the room.
Right.
That's where the ENIC, the Electronic Numerical Integrator in Computer, built in 1945, comes into play. It was the first general-purpose electronic digital computer.
And the numbers are just staggering. They reinforce how much capability has been compressed. This wasn't a desk appliance. It occupied a 50-foot by 30-foot room,
Bigger than most apartments today.
and it weighed 30 tons.
30 tons, more than 5 adult male elephants.
Yeah, and the power consumption.
Oh, it was so massive it caused brownouts in the surrounding area of Philadelphia when it was running at full tilt. The lights would literally dim.
But what's truly fascinating, beyond just the physical size, is how you programmed it.
Yes, this is the critical part. The ENIAC didn't store its program digitally in memory like modern computers do. If you wanted the ENIAC to solve a different set of equations, you couldn't just open a file.
What did you have to do?
You had to manually rearrange thousands of cables and switches on its massive patch panels. It was a physical rewiring process.
Like an old telephone switchboard, but on a massive scale.
Exactly. And it took days, sometimes weeks, to physically reprogram the machine for a new task.
So even though it was performing calculations in seconds, the cost of setting up those calculations was immense. It was incredibly fast, but also incredibly inflexible.
Precisely. This painful limitation highlighted the need for a fundamental architectural change. And this leads us to the concept that still governs all of computing today.
The stored program concept.
Credited largely to John von Neumann, he proposed that the instructions of the program should be stored in the same high-speed memory as the data.
So you're not rewiring the hardware anymore.
You're just loading new data, new instructions. This allows the machine to be reprogrammed almost instantly.
And that's the key distinction. Every smartphone, every laptop, every server running today is built on this von Neumann architecture. The ENI proved the speed gain was possible.
But the stored program concept made that speed gain useful and universal.
And speaking of physical mechanisms, we really need to clarify the difference between a computer and a robot, because that confusion persists.
It does.
Is my Roomba a computer or a robot, or both?
It's both. A robot is fundamentally a machine with physical movement actuators, wheels, arms, that is controlled by a computer.
So the computer is the brain.
The computer is the silent decision-making brain. The robot is the body, taking the computer's output and translating it into a physical action in the real world. Your Roomba uses its computer to process input from its proximity sensors, decide on a cleaning path.
And then output commands to the motors and brushes.
Exactly. So if you remove that smart chip, the motors stop being instructed and it just becomes an inert plastic object. The logic is gone.
And this entire concept of logic, of a universal machine that could be programmed to do anything, it wasn't formalized in 1945.
Yeah.
It was over a decade earlier.
That's right. We have to shine a light on Alan Turing.
The grandfather of computers.
Alan Turing, a mathematical genius working in the 1930s, conceptualized the theoretical basis for modern computing. He imagined the universal machine.
Which wasn't a real machine, right? It was a thought experiment.
A thought experiment, yes. A device that could theoretically perform any conceivable calculation, provided you fed it the right set of instructions on an infinite tape.
What's so profound about that is he proved that one single, sufficiently complex machine could be programmed to emulate the behavior of any other specialized calculation machine.
This wasn't about building a better calculator. It was about defining the absolute limits and potential of computation itself.
And that concept, the Turing machine, is the bedrock of computer science.
It proved that if a problem can be solved by a logical sequence of steps, a programmable machine can solve it. That's why he's so important. His work gave the architects of the ENIC and all subsequent machines the theoretical roadmap to follow.
Okay, so now we understand that a computer is a universal, programmable machine built on Turing's concept and von Neumann's architecture. To fully function, though, it has to perform 4 essential tasks in a continuous cycle.
Yes, the 4 superpowers: input, processing, storage, and output, or IPOS. Think of it less as a simple recipe and more as a highly structured parallel pipeline where information is constantly flowing and transforming.
Let's start with power number 1, input, feeding the beast.
Input is the mechanism by which the computer ingests data from the outside world. This involves converting physical phenomena, a key press, a voice vibration, light waves, into electrical signals the computer can understand.
Into the binary ones and zeros.
Exactly. And we often think of the most obvious devices, keyboards, mice, microphones, but the spectrum is just vast.
Much faster.
Indeed. We have digital input devices like a mouse or a keyboard that directly send discrete signals. But increasingly, we rely on analog input devices that capture continuous data, like a thermometer or a sound sensor.
So how does a computer understand something continuous, like a sound wave?
It needs a critical piece of hardware called an analog to digital converter, or an ADC. The ADC samples that continuous signal thousands of times per second and turns it into a series of discrete binary values. Without the ADC, your microphone input is just useless electrical noise to the computer.
And speaking of input devices that totally changed the paradigm, let's revisit the computer mouse. We just take it for granted now.
We do, but its introduction was a huge intellectual shift.
Douglas Engelbart's 1964 wooden mouse.
A revolutionary concept. Because prior to that, input was almost exclusively text-based command lines. If you wanted the computer to do something, you had to type a precise, logical instruction.
Which required a lot of technical knowledge and perfect syntax. One typo, and it fails.
Right. The mouse, paired with the later development of the graphical user interface, or GUI, allowed us to input commands spatially.
Pointing and clicking.
Pointing and clicking on visual representations of data. This democratized computing almost instantly, making it accessible to anyone who could point a finger, not just those who had mastered code.
And these input methods continue to evolve, specifically to make computing more inclusive.
Oh, absolutely. The need for accessibility drives so much innovation here. We noted the example of Kai in Japan using voice input to draft his poems because traditional typing presented a physical barrier. This isn't just convenience, it's enablement.
And it goes even further than that.
Of course. Consider sophisticated eye-tracking input systems. They're used by individuals with severe motor limitations where their ocular movement is the input. The cursor follows their gaze, and a long blink acts as a click.
So the computer adapts its input methods to the user's remaining capabilities,
giving them full functional access. It's incredible. The quality of that initial input then dictates the quality of the entire subsequent process. It's the foundation.
Which leads us to power number 2, processing, the thinking chip.
Once the data is input and converted into binary, it races to the CPU, the central processing unit. This is the heart of the machine, responsible for executing every single program instruction. It's not just following one recipe, it's reading a million recipes simultaneously.
We always hear about CPUs in terms of speed, gigahertz, and capacity, like the number of cores. How do those metrics translate into actual processing power?
So the clock speed, measured in gigahertz, is the rhythm or the heartbeat of the CPU. 1 gigahertz means the processor completes 1 billion cycles per second.
1 billion.
This speed determines how fast the CPU can fetch an instruction, decode it, execute it, and write the result back. A higher clock speed generally means faster sequential task completion.
And the cores, that's a term we hear everywhere now, multi-core processors.
The cores are effectively individual processing units contained within a single chip. Think of them as multiple brains working in parallel. A dual-core processor has 2 brains. A modern gaming chip might have 8 or 12.
And this allows for parallel processing.
Exactly. If you are editing a video, the computer can assign 1 core to rendering the video file, another core to managing the operating system, and a third core to playing your background music. This ability to divide labor is what yields the massive speed gains we see today.
So we're talking billions of calculations per second happening across multiple pipelines, and it's all built on those microscopic switches, the transistors.
Yes, the transistor is the fundamental unit, but they are not simply on or off switches. That's an oversimplification. They are semiconductor gates that form logic circuits.
Logic circuits.
Gates that implement Boolean logic. AND or not. For example, an AND gate only outputs a 1 if both of its inputs are 1. By combining billions of these simple logic gates, we can build complex arithmetic circuits that perform addition, subtraction, and all the logical comparisons required by a program.
And the scale of this is just, it's hard to comprehend. The most advanced chips today pack tens of billions of these tiny transistors onto a chip smaller than your thumbnail.
The density is constrained by physics. We are reaching the atomic limit of miniaturization, which is why architects are now focusing on efficiency and parallelization, more cores, rather than just pushing raw clock speed higher and higher.
Because all that miniaturization creates intense heat.
A significant challenge in maintaining speed. Managing that heat is a huge part of chip design.
But all that immense speed and complex logic is still bound by that rule we brought up. Garbage in, garbage out. GA go.
This is a philosophical truth as much as a computing principle. Because the computer lacks intuition or morality, it follows instructions perfectly. It cannot discern an illogical premise.
So if you feed it flawed, incomplete, or intentionally biased data, the garbage in.
The processing will execute flawlessly, but the output will be predictably flawed. The garbage out.
And this simple truth has profound consequences in modern applications. We see this play out constantly in fields like artificial intelligence and machine learning.
Absolutely. If a company trains an AI model, which is just a highly complex program on historical data that reflects existing human bias, the AI will learn and perpetuate that bias.
Give us an example.
Well, if facial recognition software is trained predominantly on images of one demographic, it will perform poorly when trying to identify people from other demographics. The processing unit simply calculated the correlations it was given. Its GI-GO scaled up to a massive social consequence.
The computer isn't biased.
The input data was.
Okay, so once the CPU has done its work, processed the input, executed the instructions, it needs somewhere to put the data, either temporarily or permanently. This is power 3, storage.
And we must be really precise in differentiating the two critical types of digital memory: the fast, temporary workspace and the permanent archive.
Let's start with that temporary workspace. RAM, random access memory.
RAM is the computer's short-term working memory. It stores the data and instructions the CPU needs right now to keep applications running smoothly.
And it's incredibly fast.
Incredibly fast, because the CPU can access any piece of data directly or randomly without sequentially searching through memory. This is essential for multitasking.
But RAM has a crucial physical limitation.
It is volatile. This is a key technical concept.
What does that mean exactly?
RAM stores data using tiny capacitors that hold an electrical charge representing a 1 or a 0, but these charges leak away almost immediately. So RAM chips need constant electrical refreshing just to maintain the data.
So the instant you turn off the
A
power.
refresh stops,
Yeah.
and the data is lost. It fades away like a dream when you wake up.
Which is why we need the long-term permanent archives. That's where hard drives, SSDs, and cloud storage live.
Yes. This is non-volatile storage designed to retain data indefinitely without power. Traditional hard disk drives, or HDDs, used magnetism to store data on spinning platters, a physical stable state.
And the modern standard solid-state drives, or SSDs.
SSDs use flash memory, which traps electrons in physical cells using something called floating gates. These electrons remain trapped for years without needing any power.
The difference in access speed between them is immense, isn't it?
Oh, significantly faster. HDDs are mechanical. You have to physically wait for a spinning platter to rotate under a read-write head. SSDs are entirely electronic, meaning access is almost instantaneous.
So it's the difference between finding a book in a library by looking through every single shelf versus just knowing exactly where it is.
A good way to put it, this is why upgrading from an HDD to an SSD often feels like buying a whole new, faster computer.
The historical scale shift in storage is almost as unbelievable as the shift in the CPU.
It really is. The first IBM hard drive in 1956 was the size of 2 refrigerators.
For 5 megabytes.
5 megabytes. It stored roughly 5 million characters. Today, you can buy a tiny microSD card that fits under your fingernail and holds 2 trillion characters.
That miniaturization and density have made portable computing and massive data storage feasible, and that has fundamentally changed everything.
From personal photography to global data centers.
And while storage capacity feels almost limitless now, we still run into the pitfall of clutter.
We do. Just like a messy physical room, filling your storage with disorganized files slows down performance. Even with fast SSDs, the operating system has to index and manage vast quantities of data.
And the data can become fragmented.
Stored in non-contiguous chunks across the drive. The system then has to spend extra processing cycles just retrieving those scattered pieces, slowing down the overall system efficiency. Good file management is still essential for peak computer performance.
Which brings us to the final superpower. Output. Talking back.
This is the computer's method of translating the results of its complex internal calculations back into a format that humans or other machines can understand and use.
So after all the thinking is done, the machine needs to communicate. We know the big 3. Screens, speakers, printers.
But the diversity of output has just exploded. Screens, of course, have moved from purely green and black text in the early days to high-resolution, high-refresh rate displays that render photorealistic color.
And the technology used in output has become adaptive.
Incredibly so. For example, modern operating systems can adjust screen color hues dynamically for users with color blindness, providing a personalized output.
Beyond visual, we have physical output.
Yes, the haptics in a game controller or a smartphone are critical outputs. A physical vibration that confirms a digital event, like a button press or an impact in a game.
And then there's manufacturing output.
3D printers translating complex digital CAD files into physical plastic or metal prototypes, or massive industrial robots welding cars based on programmed output commands.
That distinction, output for the user versus output for another machine, is really important.
Yeah.
The welding robot's arm position is an output signal directed at the physical world.
Precisely. And if we want to tie the entire IPOS cycle together, the simple example of opening an app on your smartphone provides the perfect recap.
Let's walk through the full computational cycle on a device we hold in our hands every day.
Okay, you input a tap on the screen to open an app.
Simple enough.
That tap signals the CPU. The CPU instantly fetches the necessary program instructions from permanent storage, the SSD, and loads them into temporary RAM for quick access.
Then the processing happens.
The processing unit executes millions of instructions per second to launch the app. Finally, the opened app, displaying its graphics and text, appears on your screen as output.
And every interaction, scrolling, tapping a button, viewing a result, is just a new iteration of that loop.
A new iteration happening so fast it feels seamless and instantaneous.
Okay, we've covered the 4 functions that define a computer. Now let's step back and play that computer hack game, realizing how integrated these machines are into our infrastructure and daily life. They are no longer just desktop boxes.
No, once you look for that IPOS cycle, you see them everywhere, often in the form of tiny, specialized microcontrollers rather than general-purpose CPUs. These are called embedded systems.
They're designed for a single, narrow task.
Right. Give us some examples of these hidden computers.
Well, we're talking about the digital clock in your microwave. You input the time setting, it processes the countdown sequence, and it outputs the command to stop heating. Simple IPOS.
Or the anti-lock braking system in your car. It uses sensors as input to detect wheel slippage, a dedicated chip for processing to calculate the required braking pressure,
And actuators as output to modulate the brake calipers hundreds of times per second.
and the infrastructure we rely on daily. Traffic management is a complex computational problem.
It is. Modern traffic lights often use embedded computers that take input from magnetic induction loops under the road to sense the presence and density of waiting cars.
And they process that information against optimized programs to output adjusted timing cycles, trying to reduce congestion during peak hours.
It extends even to our own bodies and healthcare.
Think about the tiny, life-sustaining devices. A pacemaker constantly monitors the electrical signals of the heart. That's the input.
Its internal computer processes that rhythm against a desired set rate.
And, if necessary, outputs a corrective electrical pulse to regulate the heartbeat. Similarly, advanced hearing aids take sound input, filter and process it for frequency and volume, and output a refined signal to the eardrum.
These are highly specific computers designed to manage biological input.
And the source material gives us essential reminders of how this ubiquitous technology is not just about convenience, but about global access to knowledge and economic empowerment.
Take the story of Priya in rural India. The simple access to a shared tablet, a low-cost portable computer, provides her with an output stream of global educational resources.
Right. It allows her to learn about wildlife and science in a way that would be impossible if she relied solely on local, physical books or infrastructure.
And applying that same accessibility to economic challenges.
Farmers across Africa are leveraging the power of mobile phones, which are, at their core, pocket-sized computers, to gain immediate access to vital information. They input their location.
And the computer processes data from global satellites and forecasting models.
And outputs accurate, localized weather predictions, or, critically, current market prices for their crops. This cuts out the middlemen and drastically improves their economic decision-making.
Even for scientific endeavor in the harshest regions on Earth.
The ability for scientists in Antarctica to use ruggedized, specialized computers to process complex data models on-site, whether studying ice cores or mapping penguin colonies, means they can achieve mission-critical analysis in real time.
Rather than having to wait months to return the raw data to a central lab.
The computer is designed to survive extreme input conditions to produce essential research output.
And this level of global interaction relies, of course, on connectivity, the World Wide Web.
The Internet is simply the global network that allows these scattered computers to communicate, enabling the seamless exchange of input and output. It began in 1969 as ARPANET.
Which originally connected just 4 university computers.
Right, and its core purpose was to maintain redundant communication pathways, meaning if one part of the network failed, the others could still talk to each other.
And that founding principle of decentralized communication is why the internet today is so resilient and massive.
It connects billions of devices and makes all the global examples we just discussed possible. It's a remarkable evolution.
But let's recap that crucial final pitfall from Section 1. The IPOS test must be met for a device to be a true computer.
Not all electronics are computers.
Correct. A standard electric kettle is not a computer. It simply uses a thermostat to turn the heating element off when a certain temperature is reached.
But a smart kettle is a computer.
Right, because you input a desired temperature via an app, its internal processing unit communicates with a sensor as input and outputs the command to heat the water to precisely 92 degrees Celsius.
The ability to follow a complex, changeable program based on variable input is the defining characteristic.
Okay, now that we've established the structure, we have to turn to the why. The ultimate impact of computation goes far beyond efficiency and productivity. It's about solving humanity's biggest puzzles and fundamentally transforming societal access.
Let's start with those big puzzles. The raw speed of processing allows us to ask questions that were previously just computationally impossible.
Like modeling climate change.
Absolutely. We can't run the clock forward 100 years to see the actual effects of current emissions, but we can feed petabytes of data atmospheric conditions, oceanic currents, ice core samples into supercomputers.
And these machines process billions of variables to create accurate simulation models.
And these models output highly reliable predictions, helping policymakers design effective mitigation strategies. They act as a digital laboratory.
A digital lab for problems too large or too dangerous to test in the real world.
And that applies to engineering and design as well. Designing safer infrastructure like bridges or high-rise buildings involves complex calculations of stress, aerodynamics, material failure.
Computers allow engineers to run thousands of design iterations rapidly, optimizing structural integrity before a single piece of steel is ever cut.
This speed of iteration yields better, more sustainable results.
And on the accessibility side, the personal impact is often the most profound. Computers break down barriers that once seemed insurmountable.
The stories of empowerment are immense. Consider Lena in Canada, who has limited mobility. By using voice-activated computer systems, she inputs simple voice commands.
That the computer processes and outputs as commands to her home's lights and temperature controls.
This technology restores autonomy and independence that physical limitations might have taken away.
And the distance barrier, which was once an immense financial and emotional burden, is collapsing.
Ahmed in Egypt connecting with cousins in Australia via video calls is a perfect example. Computers, through rapid processing of audio and video input and output across the network, just erase thousands of miles of physical distance,
making instant, frequent, personal connection the norm rather than the exception.
Economic barriers to education are also being systematically removed.
Sofia in Brazil is accessing free online books using a library computer. That computer, connected to the World Wide Web, acts as a democratizing gateway.
She doesn't need to afford expensive textbooks or personal hardware. The infrastructure provides the gateway to the global digital library, ensuring knowledge access is not determined by economic status.
And specifically, tailored learning solutions are transformative.
We noted Emma in the UK, who uses text-to-speech programs to help manage dyslexia. Her program takes text input, processes it, and outputs the information audibly,
allowing her to absorb complex educational material in a way that boosts her confidence and retention.
It's adaptive output tailored to cognitive input needs. Similarly, Omar in the UAE uses apps that process sign language videos and output them for clear communication and learning, bridging severe language and sensory barriers.
This entire adventure, this evolution from ENIAC to adaptive technology, was built by incredibly diverse intellectual heroes. We've mentioned Turing, but let's delve deeper into the pioneers whose work made modern programming possible.
We have to begin with Ada Lovelace in the 1840s, working alongside Charles Babbage. While Babbage designed the mechanical analytical engine, Lovelace was the one who saw its full potential.
She recognized that the machine could go far beyond simple arithmetic.
Precisely. She wrote what is widely considered the first computer algorithm, a sequence of instructions designed to be executed by the machine to calculate something called Bernoulli numbers.
So she grasped that the machine could process any logical symbol, whether it represented a number, a letter, or a musical note.
She understood the power of the program itself, conceptually laying the groundwork for all software written today.
And moving into the electronic age, we have Admiral Grace Hopper, who fundamentally solved the problem of human-machine communication.
Hopper, a genuine titan of computing in the 1950s, realized that having to write every program in tedious binary or low-level assembly language was inefficient and incredibly error-prone.
So she championed and eventually invented the first compiler.
A code translator.
Exactly. The compiler allowed programmers to write instructions in high-level languages much closer to human English, which the compiler would then automatically translate into the machine's required binary code.
This transformation dramatically accelerated programming, making large, complex software projects feasible for the very first time. She effectively made programming accessible to a wider pool of talent.
And of course, we have to include the anecdote that gives us one of computing's most enduring terms.
The famous literal bug.
Yes. Grace Hopper is credited with finding the first actual computer bug while working on the Mark II computer. It wasn't a software error, was it?
No, it was a physical moth that had flown into the machine and caused a malfunction in a relay. She taped the deceased moth into her logbook and coined the term bug for any mysterious, persistent problem in the system.
A great story. Now, having explored the immense benefits and historical drivers of computing, we have to return to a final necessity balance.
It's the final warning, the context for using these powerful tools effectively.
Computers are, and must remain, tools that enhance our lives.
They should not replace fundamental human skills or real-world interaction. We must foster critical assessment of digital information, understanding that because of GeoGo, just because an output is displayed by a computer, it doesn't mean it's true.
And especially for children, balancing screen time with physical activity, outdoor exploration, and face-to-face interaction is crucial for holistic development.
The goal is mastery of the tool, not dependence on it.
What a deep dive. We've gone from the conceptual genius of Turing and Lovelace through the room-sized ENIAC to the detailed architecture of IPOS and into the pervasive, life-changing ubiquity of computing today.
And we've realized that these machines aren't powered by magic.
They're powered by logic, by programs, and by our instructions.
And this realization that we are in control of the logic is key. We've seen how computers empower creativity across the arts and sciences. The knowledge you've gained about the CPU, RAM, and the input cycle is the foundation you need to understand future technologies, not just current ones.
So here's the provocative thought we want to leave you with, listener. Something to genuinely challenge your imagination.
If today's computers can solve global climate puzzles and connect distant families instantly, we have to ask, what seemingly impossible problem could your dream computer solve tomorrow?
And think beyond the current limitations. We've been discussing keyboards and screens, but imagine a computer that uses truly unconventional input.
Not just light or sound, but perhaps direct measurement of tectonic plate movement or environmental variables we can't currently perceive.
And what about unconventional output, like generating instant, customized medical treatments or projecting stable, interactive hologram screens?
The challenge is to leverage this fundamental IPOS knowledge and dream of a future computer that doesn't just improve current technology, but fundamentally solves a massive global hurdle. This is how current knowledge inspires truly revolutionary invention.
A perfect challenge to leave you pondering. And for those of you who want to continue this adventure, join us next time. We are literally going to look inside the machine.
Opening the treasure chest of a modern desktop computer.
We'll explore the physical components, the hardware, the chips, the buses, and the memory sticks in much more granular detail.
We'll discuss how silicon works its magic and the physical differences between that volatile RAM and the non-volatile SSD.
We'll see you on the next deep dive.